Hello there, and welcome to Science for Sleep, where the stars lean in a little closer and science whispers softly to the curious mind that can't quite switch off. Tonight, let's drift towards something that sounds fast, but is actually about limits, boundaries. The universal speed limit that nothing can break, not even light itself. You've probably heard the phrase, nothing is faster than the speed of light. It's one of those facts that sits in the back of the brain like a dusty trophy, accepted, but not always understood. But have you ever wondered why? Why light can't go faster? Why the universe put up a speed sign and said, that's far enough? Imagine a cosmic sprinter, light itself, dashing through space at nearly 300,000 kilometers per second, and yet never cheating a step beyond that. Not in a hurry, not held back, just absolute. And that, dear listener, is our mystery for tonight. But before we chase that beam of light across the cosmos, let me ask, where in the world are you listening from? And what time is it there? Is the sun still hanging low in the sky? Or has it long since slipped behind the hills, leaving you in the company of stars and quiet? If you find this little thought voyage gentle, or just a nice companion for the winding down hours, it would mean the world if you liked this video, maybe subscribed, or simply shared it with someone else who likes their science with a side of stillness. So, settle in, let your shoulders drop, let the breath ease in and out like a tide, slow your thoughts, and let's begin. Because somewhere between motion and stillness, between speed and silence, lies the story of why light, of all things, can only go so fast. There's something odd about speed, isn't there? It's not just a number or a measure of motion, it's a feeling. A sensation that lives in the body, in the breath, in the way your stomach turns slightly on a roller coaster, or how your thoughts seem to lag behind the motion of a passing train. And when we think about light, the fastest thing we know, we don't just imagine speed, we imagine instantaneousness, that flick of a switch when the room goes from dark to bright, the flash of lightning before the thunder catches up, the way headlights chase the road ahead, no matter how quickly we drive. Light feels immediate, it feels like now. But the truth is, even light takes time. It just moves so fast most of the time we don't notice. And maybe that's where the fascination begins. Not with what we can measure, but what we can't feel. When you look at the stars, those quiet flickers scattered across the night, you're not really seeing them as they are. You're seeing them as they were. Some of that light began its journey toward your eyes before you were even born, before cities were built, before some civilizations even existed. And yet, here it is, arriving just in time to be noticed. There's something deeply moving about that. A photon of light, born in the heart of a star, travelling across the black ocean of space for hundreds or thousands or millions of years, only to end its journey here in your eye. It doesn't feel slow, but it certainly isn't instant. We rarely think of light as a traveller. It just seems to be there, in the room, on your screen, on your skin. But every ray of sunshine, every beam from a flashlight, every soft glow from a candle's flame is in motion. And its speed, though extraordinary, is not infinite. But perhaps what's even stranger is that it could be. That is, when we imagine the universe, all this vast emptiness, there's nothing really to stop light from going faster. No wind resistance, no cosmic traffic. So why doesn't it? Why did nature decide that light would go just under 300,000 kilometers per second, and no more? You might ask, does that even matter to me? After all, you're not racing photons through the kitchen, or calculating nanoseconds between blinks. But here's the twist. The speed of light isn't just about beams and bulbs and sunsets. It defines time itself. When you move, when you breathe, when you speak or blink or think, Every second you experience is connected to how fast light can go. If that speed were different, faster or slower, everything about the universe would change. And not just the stars. You, your memories, your age, the way a heartbeat feels. The speed of light is woven so tightly into the fabric of reality that it isn't just about how fast something moves, it's about how anything moves at all. But that's not how we tend to experience it. For us, speed is always relative. A car zooms past, a bird dives, the wind picks up. These are things we feel, but when something moves too fast, it disappears into invisibility. Like a spinning fan, turning into a blur. Like time-lapse clouds that no longer drift but sprint across the sky. Like a bullet that leaves no trace but sound. Light does this too. It moves so quickly it hides its movement entirely. We don't see light arrive, we just see the world it reveals. And yet even light has rules it must obey. It can't skip ahead, it can't take shortcuts, it doesn't race, it glides, unchanging. No matter how hard we try, no matter how fast we fling a rocket or swirl an electron, nothing can catch up with it, and nothing can overtake it. And maybe that's what makes it feel almost divine. A limit so fundamental, even the universe can't bend it. But we humans, we don't like limits, do we? We measure, we build, we accelerate. We push boundaries, break records, and dream about faster-than-light travel, warp drives, wormholes, and shortcuts between stars. Because in our minds, limits are made to be overcome, but nature doesn't always agree. Some rules aren't meant to be broken. Some boundaries exist not to frustrate us, but to define what's possible. So maybe this question, why is the speed of light limited, is really about something deeper. Maybe it's about understanding what makes a rule unbreakable. Maybe it's about listening, not just to what's fast, but what's fundamental. Because when something moves as fast as causality itself, when it draws the line between now and later, between here and there, maybe it isn't just about speed at all. Maybe it's about the shape of reality, the shape of space, the shape of time. And maybe, just maybe, it's about us. Because when you close your eyes and remember a moment, light was there. When you fell in love under a full moon, or stared too long at the sun, or watched a flickering campfire from the warmth of a blanket, light shaped that memory. But not just the glow or the colour, the timing, how long it took for that moment to reach you. The speed of light is the speed of connection. Between cause and effect, between what is and what was, it's the reason we can remember. It's the reason we can know. So when we ask, why is the speed of light limited? We're not just asking a technical question. We're asking about the edge of change, the boundary between what can happen and what can't. And like most things in science, the moment we touch the boundary, it softens, reveals more than it hides, invites us in, not with flashing lights or roaring engines, but with a whisper, this far, no faster. And somehow that's enough to set the whole universe spinning. Long before we knew anything about photons, wavelengths, or cosmic speed limits, humans looked to the light and saw something sacred. To the earliest people, light was not a particle or a wave. It was a presence, a force, a blessing that split the world into day and night, warmth and shadow, life and the long sleep of winter. And like all things that matter deeply to us, we wrapped it in stories. In many traditions, light was the very first creation. Let there be light, say the words from Genesis. Not as a detail, but as a beginning. A command that divided nothingness into something. Other myths agree. In ancient Egypt, the sun god Ra sailed across the sky each day, his light a shield against chaos. The Greeks spoke of Apollo and his golden chariot. The Norse imagined Sol, the sun goddess, pursued by a hungry wolf, always running, always just ahead. But no one asked how fast the chariot rode. No one questioned how quickly Sol fled across the sky. Light was swift because it had to be, because darkness was always close behind. And maybe that was enough. To ancient eyes, light was already perfect. It warmed the crops, banished fear, painted the world in colour. What need was there to measure something so divine? And yet, curiosity has its own kind of gravity. At some point, someone must have stared at a flickering flame and wondered, how far can light go? How fast does it spread? Is there a delay, even a tiny one, between the spark and the shine? In early Greek philosophy, light was believed to flow out from the eyes, a kind of visual fire that reached out to touch the world. Plato held this view, so did Euclid. They thought we saw things not because of light entering the eyes, but because of something inside us reaching out, gently probing the surface of things. This theory endured for centuries, not because it was right, but because it felt intuitive. Vision was active, not passive. Seeing meant searching. It wasn't until around 1000 CE that an Arab mathematician and physicist named Ibn al-Haytham challenged that view. In his book of optics, he argued that light must come from external sources, like the sun, a candle, or a reflection, and enter the eyes, not the other way around. He used observation, experimentation, and logic. He didn't just think, he tested. And in doing so, he laid the groundwork for a new way of seeing light, not as a mystical essence, but as something that moved, that travelled, that could in theory be measured. But how do you measure the immeasurable? The idea that light might have a speed, not infinite, not divine, but measurable, was slow to catch on. Most believed that light, if it did move, must do so instantaneously. How could it not? A lantern lit in a dark room doesn't gradually brighten, it just does. There's no visible delay. So for centuries, even the best minds assumed that light was instant. Galileo disagreed. In the early 1600s, he and a partner attempted one of the first experiments to measure the speed of light. They stood on two distant hills, each with a lantern. Galileo would uncover his lantern, and when his assistant saw the flash, he'd uncover his own in response. By timing the delay, they hoped to calculate how long it took light to travel the distance. It was a clever idea, but flawed. The distance between the hills, a few kilometres, wasn't enough. Light moved too fast and their reaction times were too slow. To them it seemed instant, but Galileo was convinced it wasn't. He had touched the boundary, and even if it slipped through his fingers, he knew it was there. Nearly 50 years later, someone did catch it. In 1676, a Danish astronomer named Ulrummer noticed something curious about Jupiter's moons. Specifically, one of them, Io, seemed to appear slightly early or late depending on Earth's position in its orbit. The further Earth was from Jupiter, the later the moon appeared. When it was closer, the moon was early. Römer put two and two together. He realised that the difference wasn't in the moon's motion, but in the light bringing the image to Earth. Light, he concluded, had a finite speed. It took time to travel the extra distance when Earth was farther from Jupiter. And just like that, the myth of instantaneous light began to dissolve. Römer didn't know the exact speed, but he'd opened the door. A few decades later, in the 1720s, an English astronomer named James Bradley refined the measurement further, using the phenomenon of stellar aberration, how stars appeared to shift due to Earth's motion. He was able to estimate the speed of light with greater precision, and slowly what had once been a mystery wrapped in myth began to take on numbers, units, equations. But even as the math grew sharper, the wonder remained, because every time scientists tried to pin light down, it danced just out of reach. Was it a wave? Was it a particle? Did it ripple through space like water across a pond, or shoot out in tiny bullets? The answer, famously, became both. In the 19th century, James Clerk Maxwell gave us a new understanding. He described light as an electromagnetic wave, a self-propagating disturbance in electric and magnetic fields. His equations predicted a wave that travelled through space at exactly 209,592 kilometres per second. It was a remarkable result, but it came with a strange implication. If light was a wave, it had to move through something. All known waves did. Sound through air, water waves through water, even seismic waves through rock. So what was light's medium? Physicists called it the luminiferous ether, an invisible substance that supposedly filled all of space, allowing light to ripple through it. But then came the Michelson-Morley experiment in 1887. They built one of the most precise instruments of their time, an interferometer, to detect Earth's motion through the ether. The idea was that light would move slightly faster or slower depending on our direction of travel through this invisible sea. But the result? Nothing. No change. No ether. It was a crisis. And into that crisis stepped a young patent clerk named Albert Einstein. But that's a story for another section. Still, even long before Einstein, human beings had already begun the journey, from myth to measurement, from chariots and goddesses to equations and observatories, and across cultures, light was always more than just light. In Hinduism, light is knowledge. The festival of Diwali celebrates the triumph of light over darkness, not just literally, but metaphorically. Wisdom over ignorance, hope over despair. In Buddhism, the lamp of wisdom is a symbol for enlightenment. In many indigenous traditions, light is not separate from life. The sun, the flame, the reflection on water, these are not just phenomena, they're beings, teachers, guides. Even our language is full of luminous metaphors. We say someone sheds light on a topic, or that an idea dawns on us. We see the light when we come to understand something. We call insights brilliant. We associate brightness with clarity, with truth, with joy. And what speed, if not the yearning to reach those things, to find clarity, to close distances, to understand faster. Maybe that's why the speed of light holds such a strange place in our imagination. It's not just a number, it's a ceiling, a horizon, something to chase, and also something to accept. Because light, in all its ancient power and modern complexity, doesn't rush. It doesn't bend to our will. It just moves, perfectly, inevitably, at a pace that defines the shape of time itself. So while we once sang songs to the sun, we now chart the paths of photons. We still marvel. We still wonder. And somewhere between the myths of Ra and the math of rumour, between Apollo's chariot and Maxwell's fields, we keep returning to the same truth. That light, in all its beauty, moves through time and space with a kind of calm urgency. Fast enough to illuminate, slow enough to experience, limited, yes, but limitless in meaning. When we talk about the speed of light, we tend to picture light doing something. Moving, travelling, arriving, like a cosmic courier, darting across the vacuum of space to deliver images, energy, warmth. But what if I told you the speed of light is not just about motion? It's about the architecture of reality itself. Because that number, 299,792 kilometers per second, isn't random. It isn't arbitrary. It's not even chosen by light. It's chosen by space and time. And to understand why light has a speed limit, we have to look deeper, not at the light itself, but at the stage it moves across. Let's begin with Einstein. Before he entered the picture, most scientists believed that time and space were absolute, that everyone, everywhere experienced them the same way. 1 second for you was 1 second for me. 1 meter here was 1 meter there. It was a comforting idea, predictable, logical, but it was wrong. In 1905, Einstein published his theory of special relativity, and in it, he proposed something revolutionary, that space and time are not separate. They are part of the same thing, a unified fabric we now call spacetime, and this fabric can stretch, it can warp, it can twist. Not only that, but your motion through it changes how you experience time, space, and even mass. But here's the twist. In this malleable universe, there is one thing that remains constant no matter what: the speed of light. Light, Einstein showed, always travels at the same speed in a vacuum, regardless of who's watching or how fast they're moving. Imagine that. A car moves faster or slower depending on the road, the engine, or how hard you press the pedal. But light is stubborn. It refuses to change. It will always move at that precise speed, even if the observer is running away from it or chasing it down at nearly light speed themselves. But why? To answer that, let's look closer at what light actually is. Light is a form of electromagnetic radiation, a wave made of oscillating electric and magnetic fields dancing together in harmony. James Clerk Maxwell in the 19th century wrote down the equations that describe how these fields interact. And when you solve them, something astonishing emerges. Electromagnetic waves must move at a particular speed. And what is that speed? Well, it depends on two fundamental properties of the vacuum of space: the electric permittivity and the magnetic permeability. These are constants that describe how electric and magnetic fields behave in empty space. When you plug those values into Maxwell's equations, out comes a number: 292,458 meters per second, the speed of light. In other words, light speed isn't just a property of light, it's a property of space itself. The vacuum of the universe, even when it's empty, silent, and dark, has a structure. It has rules, it has resistance, and those rules determine how fast light can go. You can think of it like a guitar string. The string has tension, it has length, it has thickness. All of these define how fast a wave can travel along it. You can pluck it harder or softer, but the speed of the wave is set by the string's nature. Space is like that. No matter how empty it seems, it has a deep underlying structure, and that structure sets the limit for how fast electromagnetic waves, including light, can move. It's not that light is hitting a wall or dragging its feet, it's that the medium it moves through, even when that medium is a vacuum, has rules, and those rules are baked into the very shape of reality. But there's another reason the speed of light matters, and this one is even more profound. Because in Einstein's universe, the speed of light isn't just a speed, it's a boundary, a cosmic speed limit. Let's imagine you're in a spaceship flying through the void. You press the thrusters, accelerate faster and faster. As you approach the speed of light, strange things begin to happen. Your mass increases. Time slows down for you relative to people back on Earth. Distances contract. But no matter how much energy you use, how hard you push, you'll never quite reach the speed of light. It would take infinite energy, and you'd become infinitely massive. Which is a poetic way of saying, the laws of physics won't let you do it. Why? Because the speed of light isn't just the speed of light, it's the speed of causality, the fastest that any information can travel, and that's key. If you could travel faster than light, you could, in theory, arrive at a place before you left. You could cause effects to happen before their causes. You could break the order of time, and that, the universe seems to say, is off limits. The speed of light is the line in the sand, the barrier that keeps cause before effect, questions before answers, footsteps before echoes. It's not a speed like running or flying or launching a rocket. It's a rule about how the universe unfolds, and the closer you get to breaking that rule, the weirder things get. Time dilates, clocks tick slower, your perception warps, and though you may feel like you're moving forward to the rest of the universe, your journey is being stretched into something more like a loop, a paradox waiting to happen. So rather than letting that happen, the laws of physics put up a wall, a quiet, elegant wall. No lights, no sirens, just an equation softly whispering, "That's far enough." And here's something else to consider. If the speed of light were different, even slightly, the universe as we know it wouldn't exist. Stars wouldn't burn the same. Atoms wouldn't hold together. chemistry, biology, life. All of it would unravel. That number isn't just a ceiling, it's a foundation. And yet, in everyday life, we don't notice any of this. Light seems instantaneous. When you turn on a lamp, the room fills without delay. When you speak, your voice carries to a friend across the room with barely a pause. We live at such slow, gentle speeds that the effects of light's limit are hidden, like mountain peaks far beyond our horizon. But they're still there. They shape everything from the tick of your watch to the orbit of GPS satellites, from the glow of a candle to the whispers of ancient starlight. And here's something quietly beautiful. The reason we see anything at all is because light doesn't move infinitely fast. If it were instantaneous, every moment would be a blur. Every photon would arrive at once, layered over itself like a painting smeared by too many brushstrokes. But because light takes time, there's sequence, there's past, there's present, there's motion. The delay is what creates the dance, and in that sense, the speed of light gives birth not just to sight, but to story, to change, to memory. The fact that light takes time means the universe can unfold, can grow, can surprise. So perhaps we should stop thinking of the speed of light as a restriction and see it instead as a rhythm, not a limit, but a tempo, a heartbeat against the silence of space. Let's return just for a moment to that idea. That light is not just fast, it's the fastest anything can go. And not only that, it's the fastest anything can happen. The speed of light is the upper boundary of influence. It's not just about motion, but about messaging. No information, no signal, no push, no change can ripple through the cosmos faster than light allows. This becomes especially powerful and strange when we think about the concept of now. We tend to imagine now as something universal, the current moment, a global truth. But in relativity, now is slippery. If you and I are standing still together, we can agree on what's happening now. But if one of us begins to move, to fly, to orbit, to accelerate, our versions of now begin to drift apart. We will disagree on the order in which events occur, on what is simultaneous, and what comes before or after. And the thing that defines these boundaries, that determines what we can and can't influence in time, is the speed of light. Imagine yourself at the centre of a sphere made not of glass or metal, but of causality. Its edges are defined by how far light can travel in a given moment. Anything inside the sphere, any event, any change, you can affect. It's within your causal reach. Anything beyond? It's unreachable. Not because it's distant, but because not enough time has passed for your influence to get there. This is called the light cone. It's not something we see, but something we live inside constantly. A shape made by time and light, defining what's possible. In this way, the speed of light becomes more than a number. It becomes a boundary between the possible and the impossible, between what can be known and what must remain a mystery, at least for now. And this limit isn't just philosophical, it's practical. When astronomers observe a galaxy 1 billion light years away, they aren't seeing it as it is. They're seeing it as it was 1 billion years ago, because that's how long the light has taken to reach us. In a very real sense, telescopes are time machines, and yet they only look one way. We can see into the past. We can never peek into the future. Because light, though fast, is not infinite. It brings us the story of the universe, but always a little late, always gently delayed. There's something poetic about that. The idea that the cosmos is always arriving, always catching up to itself, and perhaps so are we. Now, let's pull back, just a little more. Einstein's later work, General Relativity, took things even further. He realized that the presence of mass, stars, planets, black holes, actually bends the very fabric of spacetime. It curves the path that light takes. It slows time down in deep gravitational wells. And yet, even here, the speed of light remains constant, not from every perspective. If you're standing near a black hole, time itself slows down for you, but light, from your perspective, still moves at the same speed. And that is the strange genius of relativity, that light speed never changes, but time and space themselves do. To preserve light's perfect pace, the universe reshapes itself, distances stretch, clocks slow, mass increases, all to ensure that this one rule remains untouched. Nothing outruns light, because if anything did, if we could send a signal faster than light, it could arrive before it was sent. It could create paradoxes, undo cause and effect, unravel the careful weave of reality. So the universe defends this boundary fiercely. You might wonder, how do we know? It sounds theoretical, abstract. But this limit shows up in places we rely on every day. Take GPS satellites. They orbit Earth, high above the surface, and because they move fast and because they're farther from Earth's gravitational pull, time moves differently for them. Tiny fractions of a second tick more slowly, or more quickly, than they do here on the ground. If we didn't account for that, your GPS wouldn't just be off by a few meters, it could be off by kilometers in minutes. So scientists correct the clocks on those satellites using Einstein's equations, because the difference in time caused by gravity and speed is real, and that difference exists because of the speed of light. Every delay, every correction is about keeping your position and time in sync with a universe that stretches and bends around that ultimate speed. And still, it holds. No experiment has ever found anything faster. Nothing has broken the limit. It remains quiet and unshakable, like the silence between stars. But here's a thought that might feel strange, even a little haunting. Light moves at light speed because it has no mass. Mass, in physics, is a kind of inertia. It resists motion. It's what makes acceleration take energy. But light has no rest mass. It doesn't need to be pushed. It doesn't need fuel. It simply is. And because of that, it always travels at that one perfect speed. Not almost. Not sometimes. Always. It doesn't ramp up. It doesn't cruise. It doesn't coast. It exists only in motion. And to the light itself, time does not pass. If you could become a photon, you would never experience the journey. From your perspective, the moment you leave a star is the same moment you arrive in someone's eye, across a galaxy. No time elapses, no distance stretches, because at the speed of light, space-time collapses. That's what the equations say. But we are not made of light. We have mass. We live in time. We take the long road. And maybe that's what makes the question beautiful. We are creatures who can't go that fast, wondering about something that can't go any slower. And yet somehow it binds us together. Because without that limit, we'd have no frames of reference, no cause and effect, no ticking clocks, no shared moments. Without that cosmic speed, that delay, that breath, we would lose the rhythm that makes stories make sense, the rhythm that lets us ask what came before or what happens next. So if you ever find yourself staring at a star or flicking off a lamp or watching the sun rise through your window blinds, just remember, the light that touches your skin has come a very long way, and it did so, not instantly, not infinitely, but at the one speed the universe allows, not a sprint, not a race, just a quiet, unwavering glide through space and time. By now you might be wondering, if the speed of light is the universe's limit, its golden rule, its unwavering heartbeat, then what happens when things get close to it? What does reality do when you push against the edges of that cosmic envelope? Let's begin with the most fundamental question of all. Why does having mass prevent us from reaching light speed? When an object with mass accelerates, whether it's a car, a satellite, or a single lonely proton, it takes energy. The faster you want it to go, the more energy you have to give. And this isn't just mechanical energy like pushing a swing. It's relativistic energy, energy that grows not linearly but exponentially. The equations tell us something strange and absolute. As you get closer and closer to the speed of light, your mass effectively increases. Not in the "I ate too much pasta" way, but in the way the universe sees you, as heavier, harder to move, more resistant to acceleration. So to reach the speed of light, you'd need infinite energy, and no matter how many solar panels, rocket boosters, or clever tricks you bring along, infinity doesn't fit into your pocket. This is why nothing with mass can ever touch that sacred threshold. Not even electrons and particle accelerators, pushed to 99.999% the speed of light, can break through. They always stop just shy, forever asymptotic, forever chasing. Meanwhile, light itself doesn't chase anything. It simply is. It doesn't accelerate, it doesn't decelerate. It doesn't experience time or distance. It emerges from a star, a lamp, a supernova, already at full speed, already gliding. So that's the first piece of the puzzle. A kind of universal agreement. Mass and light speed don't mix. The more of one, the less of the other. But there's more to explore. Let's talk about gravity. Gravity, you may remember, isn't a force in the traditional sense, not like a push or a pull. In Einstein's view, gravity is what happens when mass bends spacetime, and objects, including light, simply follow the curves. That means light doesn't escape gravity's influence. It doesn't accelerate or slow down per se, but it changes direction. It bends. This was confirmed in 1919 during a total solar eclipse. Astronomers observed that the positions of stars near the Sun appeared slightly shifted, not because the stars had moved, but because their light had curved around the Sun's gravity on its way to Earth. It was a quiet moment of profound confirmation. Gravity touches even the untouchable, but gravity can do more than bend light. It can also slow time. Near a massive object, say a neutron star or a black hole, time itself flows more slowly relative to less intense gravitational fields. So when light escapes a gravity well, it appears to us as redshifted, stretched out, its frequency lowered, as if it's expending effort to climb out of that curved space-time. This doesn't mean light changes speed. Remember, it always travels at c, the constant, but the way we experience it changes. This concept is called gravitational redshift, and it's not just theory. We've measured it with satellites, with precision clocks, even in labs using vertical shifts of just a few centimeters. Yes, clocks on a high shelf tick just slightly faster than those on the floor, because gravity is just that persuasive. Now, what if we try to stop light? It turns out you can. Not in the vacuum of space, but in certain materials light slows down dramatically. Glass, water, diamond, they all reduce the speed of light compared to a vacuum. Not because light is struggling, but because it's constantly being absorbed and re-emitted by the atoms in the material. It's like a crowd of people parting and reforming as a dancer passes through. In one experiment, physicists managed to slow light down to just 17 meters per second by passing it through a cloud of ultra-cold atoms, and in another they briefly stopped it entirely. So light speed isn't fixed everywhere, only in a perfect vacuum. But the universal constant we refer to, that 297,458 ms, is not about glass or fog or diamonds. It's about pure emptiness, the untouched stage on which all light begins its journey. This brings us to an idea that's easy to miss, but quietly thrilling. Light isn't the only thing that obeys the speed limit. Every causal influence, every signal, every force, every wave that transmits information is limited by that same speed. This means that nothing in the universe knows. Something has changed until light has had a chance to tell it. Imagine a star exploding 100 light years away. The light from that event and the knowledge of its occurrence won't reach Earth for 100 years. Until then, for all we know, the star is still there, shining silently. That delay isn't a failure of communication. It is the communication, Even gravity follows this rule. When the sun shines on Earth, we feel its warmth after about 8 minutes, because that's how long its light takes to reach us. But if the sun were to vanish, don't worry, it won't. We wouldn't feel the gravitational effects instantly. They too would take 8 minutes to reach us, because gravity, like light, is not a whisper through nothing. It's a ripple through space-time, and ripples have limits. This was beautifully confirmed in 2015, when scientists detected gravitational waves, ripples from 2 merging black holes a billion light-years away. The waves arrived at Earth, carrying news of a collision older than humanity itself, and they did so at the speed of light. So it's not just a rule about photons, it's about reality's refresh rate, the rate at which the universe updates itself. Not in jumps or bursts, but in a smooth, continuous wave, always at sea, the cosmic constant. And then we come to the anomalies, the edge cases, the strange shadows at the boundary of what we understand. For example, quantum entanglement. You've likely heard of it. 2 particles, once linked, remain connected no matter how far apart they drift. Measure one, and the other knows immediately. Spooky, right? Einstein thought so. He called it spooky action at a distance, and he didn't like it. It seemed to break his speed limit, to suggest that information was travelling faster than light. But here's the catch. No usable information is actually transmitted. The correlation is real, but it doesn't allow for faster-than-light messaging. You can't send a signal using entanglement. Only verify that 2 things are mysteriously aligned. So relativity and light speed survives, but it does raise strange questions about non-locality, about how the universe might be more deeply connected than simple cause and effect allows. Then there's Cherenkov radiation, a beautiful phenomenon where particles travel through a medium faster than light can move through that same medium. In water, for instance, the speed of light drops significantly. A charged particle, moving faster than light's local speed in water, emits a glowing blue halo, a kind of optical shockwave, like a sonic boom, but made of light. It looks like the rule is broken, but only because context matters. The particle isn't breaking the universal limit, it's just passing the local one. The true cosmic limit, the speed of light in a vacuum, still holds, and yet these edge cases remind us that the boundary is alive. It's not a fence, cold and fixed. It's a membrane, shimmering and complex, a rule that bends just enough to allow mystery. So where does that leave us? Light isn't just fast, it's the measure of fast. It defines what can be known and when. It holds the structure of reality together like threads in a cosmic loom, and every attempt to push past that boundary, whether with particles, equations, or curious dreams, brings us back to the same realization. That the limit isn't there to frustrate us. It's there to hold the universe together. Let's follow the path of a single photon now. A tiny bundle of light energy, birthed perhaps from the burning heart of a distant star. It leaves home, begins its journey across billions of kilometers of vacuum, and does what all photons do. It travels straight. Not curved, not spiraled, not meandering, unless space-time itself tells it otherwise. Because here's the next beautiful twist in our story. Photons don't choose their paths. They follow what physicists call geodesics, the shortest distance between 2 points in a curved space. And when gravity is strong enough, those paths curve not because the photon is turning, but because space itself is bent. This is why light bends around stars, why it cannot escape a black hole, why it arcs through warped galaxies like thread pulled through a loom that's been folded. We call this the gravitational lensing effect, where massive objects act like cosmic magnifying glasses, bending the light of galaxies behind them and creating arcs, rings and echoes in the night sky. It's not an illusion. It's the direct fingerprint of curved space-time, and light, always moving at the same speed, obediently follows those bends, even when the path twists like a spiral staircase, even when the destination becomes unreachable. and in these extreme places, near neutron stars or the lip of a black hole, photons can get trapped. They can enter photon spheres, orbits made of nothing but light circling endlessly, never escaping, never falling. A photon caught in gravity's grip, locked in an eternal dance. What a haunting, beautiful image. Light that never lands, never fades, never moves forward, just spins in silence forever. And here we bump against the edges of meaning. Because if light can be caught in a loop, if it can circle forever without ever reaching us, what else lies just beyond our reach? This brings us to simultaneity, the idea of now once again. In Newton's world, it was simple. Two things happen at the same time, or they don't. A fixed, global clock ticks out truth, but relativity whispers something stranger. What's now for you may not be now for me. Depending on how fast you're moving or how deep in a gravity well you are, your perception of when things happen will shift. This isn't philosophical musing, it's hard physics. Two observers watching the same pair of events might disagree about their order. One sees the first firework burst before the second, the other sees the second go first. And the thing that defines how that disagreement works, the thing that sets the limit, the boundary, the transformation, the speed of light, it defines the slope of those light cones we mentioned earlier, those invisible pyramids in space-time that determine what you can affect and what can affect you. If something lies outside your light cone, it might as well not exist. Not yet. You can't reach it. You can't send it a message. You can't even know it's there. And that's why causality, the sequence of events, depends entirely on c. So when we say that light's speed is a constant, we're also saying there is a limit to knowing, a soft wall around every moment, a cosmic whisper that says, you'll see when it's time. Now let's revisit that age-old question. Could we ever go faster than light? We've already said that nothing with mass can accelerate to light speed. But what about things that were already faster, that never slowed down, that never dipped below the limit? Could such things exist? Physicists have speculated about such particles. They even have a name, tachyons. Tachyons, if real, would always move faster than light. They could never slow down enough to reach light speed, because they'd have to lose infinite energy to do so. They'd exist perpetually outside our light cones, in a place where cause and effect start to fray. But so far, tachyons remain purely theoretical, mathematical curiosities rather than observed realities. No experiment has ever detected one, and many physicists think they'd introduce more problems than they solve, like backward causality, paradoxes, and violations of energy conservation. So the speed limit holds. Still, the idea tickles the imagination. What would a universe with faster-than-light travel look like? Would messages arrive before they're sent? Would cause bow to effect? Would you wake up before you fell asleep? In the realm of science fiction, the answers are playful. Warp drives, hyperspace lanes, wormholes. They all rely on ways to bend space, rather than outpace light. Because even fiction respects the rule, it just dreams around it. In reality, physicists have explored ideas like the Alcubierre drive, a hypothetical method of compressing space in front of a ship and expanding it behind, allowing the vessel to ride a wave of space-time itself. Technically, in this model, the ship never moves faster than light locally. It's space-time that does the moving, but the energy requirements are astronomical. It would require something we haven't found. Negative energy density, exotic matter with properties unlike anything we've ever observed. A beautiful idea, but for now, a bedtime story for telescopes. Still, it shows us something vital. Even the most imaginative minds bend over backwards to preserve light's limit, not because they want to, but because the math leaves no wiggle room. That's far enough, the universe says again, and we listen. Because maybe that wall isn't there to trap us. Maybe it's there to shape us, to give time its arrow, to give memory its direction, to give life a frame, a stage to act upon. We couldn't live in a universe without limits, because without them, there would be no boundaries, no differences, no progression, no before or after. And so, light speed, this quiet, invisible rule, gives us more than we realize. It gives us clocks, it gives us space, it gives us sequence. And somehow, in giving us what we can't do, it gives us meaning. So the next time you glance at a shadow, or feel the sun's warmth on your face, or squint into a headlight at night, remember, you're not just basking in illumination. You're witnessing a promise kept, a photon's faithful journey across the universe, obeying a limit that has never been broken, never even bruised. A light that could have tried to outrun causality, but never did. Because even the fastest thing we know doesn't try to be first, it just tries to arrive. History, when told through the lens of science, is not a straight road, but a path of gentle curves, quiet detours, and moments of starlit revelation. The story of how we came to understand the speed of light is not just a tale of measurements and equations, it's a story of patience, of watching the skies, of asking the universe a question so subtle it took centuries to hear the answer. Let's begin in a time when light wasn't even thought to move at all. To the ancient Greeks, light was mysterious, but not mysterious in motion. The prevailing idea was that sight came from the eyes themselves, beams or rays projected outward to touch the world and return impressions back to the soul. Plato supported this notion, and even thinkers as rigorous as Euclid built geometries on the assumption that vision was an outward act. But there were hints, even then, that light was doing something more than simply emerging from us. The philosopher Empedocles proposed that light moved, that it took time to reach the eye. He was dismissed. After all, how could something so fast not be instant? In the centuries that followed, theories shifted. In the Islamic Golden Age, a brilliant mind named Ibn al-Haytham challenged the Greek view. He proposed that light came from luminous objects, entered the eye, and travelled in straight lines. He described how mirrors and lenses worked. He tested shadows, reflections, and refractions. His work, compiled in the Book of Optics, became one of the foundational texts in the history of vision and light. And though he still couldn't measure the speed of light, he shifted the direction of the conversation. Light now came from the world, not the self. It had motion. It had behaviour. Still, motion isn't the same as speed. That would take much longer to grasp. Centuries passed, telescopes were invented, stars were charted, and in the early 1600s, Galileo, that restless observer of moons and motion, decided to test the speed of light with lanterns and hilltops. His method was charmingly simple. 2 observers with covered lanterns placed on distant hills. One would uncover theirs, and the other would respond as soon as they saw the light. Measure the delay, subtract the reaction time, and you could, perhaps, catch a glimpse of light's true speed. But it didn't work. Light, even across hills, moved too fast to measure this way. Galileo could only conclude that its speed, if not infinite, was at least extraordinarily great. And so, for a while, the speed of light remained more myth than measurement. Then came Ole Rømer, a Danish astronomer, born under cold skies and curious stars. In 1676, while studying the motion of Jupiter's moon, Io, Rømer noticed something peculiar. Io's eclipses didn't always follow the same schedule. Sometimes they were early, sometimes they lagged, but they weren't random. They followed a pattern, shifting with Earth's distance from Jupiter. From this, Rømer made a bold claim. The variations weren't in the moon's orbit, but in the time it took for light to reach us. Light, he said, travels at a finite speed. He even offered a rough calculation. Light takes about 22 minutes to cross the diameter of Earth's orbit. Crude by today's standards, but revolutionary at the time. Suddenly light wasn't instantaneous. It was fast, unimaginably so, but not infinite. It had a pace, a journey. And with that idea, the door to measurement creaked open. In the early 18th century, James Bradley refined the approach with a different phenomenon: stellar aberration. As Earth moved through space, the apparent positions of stars shifted slightly, not because the stars moved, but because light, arriving at an angle, created a visual offset. It's the same reason rain appears to fall diagonally when you're walking. You're moving through it. From the angle of this aberration, Bradley was able to calculate the speed of light with surprising precision, about 301,000 kilometers per second. Not perfect, but beautifully close. For the first time, light speed wasn't just an idea, it was a number. Later in the 19th century, Fizeau and Foucault, two French physicists with a flair for clever apparatus, brought the measurement into the laboratory. Fizeau used a rotating cogwheel and a beam of light aimed at a mirror several kilometers away. As the wheel spun faster, there came a point when the returning light would hit a tooth instead of a gap, vanishing from view. From the speed of the wheel and the distance of travel, he calculated light speed more precisely than ever. Foucault refined the method further, replacing the cogwheel with a rotating mirror. His setup was more compact, less dependent on long-distance reflections, and yielded a remarkably accurate value. Now light speed was not only known, it was measurable, repeatable, trusted. But a deeper mystery remained. What kind of thing was light? Was it a wave, like sound or water? Or was it a stream of particles, like tiny bullets of energy? Newton had believed in particles, corpuscles he called them, but others, like Huygens, championed the wave view. For a while, both theories coexisted uneasily, and then, in the 1860s, James Clerk Maxwell entered the stage. With a flurry of equations and a sense of wonder, Maxwell described how electric and magnetic fields interact, how a changing electric field creates a magnetic one, and vice versa. When those fields oscillate together, they produce a self-sustaining wave, electromagnetic radiation, and when you solve Maxwell's equations, you get a speed. The speed of this wave, determined purely by the properties of space, came out to exactly the value of light speed. It was an astonishing moment. Not only did Maxwell unify electricity and magnetism, he also showed that light itself is an electromagnetic wave. Suddenly, light wasn't just a mystery, it was a ripple in the very structure of reality. But that raised another question. If light is a wave, what does it move through? All known waves need a medium. Sound needs air. Water waves need water. So what about light? Physicists proposed something called the luminiferous ether, an invisible substance that filled the universe, a still sea through which light could ripple. It seemed reasonable, elegant even. Until Michelson and Morley tried to detect it. Their experiment, conducted in 1887, used an interferometer, a device that split a beam of light and measured its travel time in different directions. If Earth were moving through the ether, light should take slightly longer in one direction than another, like swimming upstream or downstream in a river. But no matter how carefully they measured, they found no difference, no ether. Their result was described as the most famous failed experiment in history, because in failing, it shattered an idea and cleared the way for something new. Enter Einstein. In 1905, he proposed a radical idea. There is no ether, no fixed stage, no privileged frame of reference. Instead, the speed of light is constant, not just in a vacuum, but for all observers in all frames of motion. To preserve this constancy, space and time themselves must bend. Lengths contract, clocks slow down, mass increases, all to keep light speed the same, no matter who watches or how fast they travel. And so, from this one principle, the constancy of light speed, Einstein built special relativity. It rewrote the rules of motion, it fused space and time, and it elevated c, the speed of a light in a vacuum, to something almost divine, a universal constant, a limit built into the geometry of space-time itself. Later, In 1915, he extended these ideas into general relativity, showing how mass and energy bend space-time, how gravity is not a force but a curve, and how light, always moving at the same speed, still follows those curves like a river through a canyon. By the mid-20th century, light's speed wasn't just known, it was fundamental. It became the definition of the meter, the basis for timekeeping, the heartbeat of satellites and atomic clocks. And in 1983, the speed of light was no longer something we merely measured, it was defined. Exactly 299,692, 458 meters per second, by decree. Not because the number changed, but because it became the anchor, the fixed point, the yardstick by which we'd now measure the world. All this, from starlight delays to rotating mirrors, from wave-particle debates to warped space-time, has led us here. To a world where your phone can find your location because of Einstein, where spacecraft navigate by timing light pulses, where we measure the universe by watching light stretch, bend, and redden as it moves through expanding space. And through it all, the speed of light remains, not just a number, not just a feature of light, but a reminder that understanding takes time, that truth reveals itself in stages, that the most meaningful limits are not those we resent, but those that shape the dance. The speed of light is the universe's way of saying, there's an order to things. That knowledge, like light, arrives in its own time, and if you ever feel frustrated by how long something takes, to learn, to grow, to reach across a distance, just remember, even the fastest thing in existence takes time to arrive, and sometimes the waiting is the most beautiful part. There is a kind of strangeness in asking why something so fundamental just is. The speed of light, that hard, elegant number etched into the bones of physics, feels more like a law than a mystery. And yet, when you sit with it, soften into it, breathe into the question, you begin to sense its deeper weight. Why that speed? Why any speed? And why should it matter so much that the universe holds it so tightly, like a secret it refuses to let go? Perhaps it's not the speed itself that is strange, but the need for a limit at all. Why can't things move infinitely fast? Why can't a thought, a particle, a heartbeat jump from here to there with no time between? It's tempting to imagine a reality where that's possible. A universe with no waiting, no delay, no causality stretched across distance. But would that be a universe we could even understand? Because speed, after all, is not just about motion. It's about change. And change needs time. It needs before and after. It needs the space between what was and what is becoming. And light, in its perfect constancy, draws that boundary for us. It says, here is what can change now, and here is what must wait. It gives the universe rhythm, sequence, story. Without that speed, maybe there'd be no narrative at all. No way to say this came first and that came next. No memories, no futures, just a blur. And all at once that means nothing, so maybe the speed of light isn't a constraint, maybe it's a gift. A way for the universe to unfold gently, moment by moment, rather than all at once. Still, there are deeper questions beneath even that. Some physicists wonder if c, the speed of light in a vacuum, is truly constant, or just constant now. Could it have been different in the early universe? Might it change, slowly, over the course of cosmic history? There are theories that say yes, that in the first breath of the Big Bang, light may have travelled faster, that this early acceleration helped smooth out the wrinkles in space-time and allowed matter to distribute more evenly. It's still speculation. The equations work either way, but it leaves us with a haunting possibility that even the constants we take for granted might have a past of their own. And if C can change, even slightly, even slowly, what else might shift beneath the surface of things? Perhaps the very structure of space-time is still evolving. Perhaps the rules we know are only one frame in a much larger reel. This opens the door to another idea, that time itself is not fundamental. Some physicists, like Carlo Rovelli, suggest that time may not be a basic ingredient of the universe, but an emergent one, something that arises only when we look at the world in a certain way, like temperature. An individual molecule doesn't have a temperature, but trillions of them moving together, that's heat, that's cold, that's weather, so maybe time is like that. Not a thing that exists, but a story we tell when we look at change. And if that's true, then the speed of a light isn't just a measure of motion, it's the rate at which we experience that illusion. The ticking of a watch, not because time is real, but because change flows in a way we can perceive. But this raises another question, one even stranger. If time is an illusion, then what does it mean to move? To speak? To be? After all, we don't experience the world as a collection of frozen frames. We experience becoming, motion, memory, desire, the ache of waiting, the comfort of progress. If time isn't real, or not fundamentally real, then our whole experience of light and its speed and its limits might be a kind of dream. A very convincing one. Still, not all physicists are so ready to let time go. Others argue that time is more than emergent, that it's woven into the structure of entropy, the arrow of disorder, and that the speed of light exists to hold that arrow steady. That c is the tempo by which the universe expands, forgets, evolves, decays. Too fast, and entropy would have no grip. Too slow, and nothing would ever change. In that view, the speed of a light is not just about causality or space. It's about meaning. It's about making time feel real to us. Creatures who live in the forward motion of memory and loss and wonder. And then, there are those who go even further. Physicist Julian Barber, for instance, argues that time doesn't exist at all, that the universe is made up of countless nows, snapshots of the cosmos, and that what we experience as the passage of time is just our movement through these frozen frames. He calls this idea Platonia, a timeless realm of possible configurations, all that ever was and ever could be, laid out not in a line but a landscape. In this vision, light doesn't move. It's just there, in each frame, in each possible arrangement. The speed we assign to it, c, is just the way we step through those frames. Like a storybook being flipped one page at a time, if Barber is right, then light speed isn't a property of reality. It's a symptom of how we read it, a whisper of how consciousness carves motion out of stillness. And that brings us to something even more slippery, the role of the observer. Because in quantum mechanics, the strange, shimmering world of particles and probabilities, the act of observation changes things. Photons can behave as particles or waves. Electrons can be here or there until you look. Some interpretations suggest that reality isn't fully real until it's measured, that you're part of the equation. And in that case, what does the speed of light really mean? If nothing is definite until observed, then perhaps light's speed isn't a rule of the universe, but a condition for experience. A threshold that defines not what exists but what can be known. A bridge between the possible and the perceived, between mystery and memory. And that brings us full circle, not just to physics, but to wonder. Because what we're really asking when we ask about the speed of light is, why is there order at all? Why doesn't the universe just collapse into chaos, or blur into white noise, or flash into being and then vanish? Why does it unfold, slowly, deliberately, in a way we can watch? Maybe it's because of light. Maybe light's limit is the metronome of meaning, the tick of the clock that gives shape to dreaming. Not too fast, not too slow, just right. So we can gaze at galaxies and feel awe. So we can remember yesterday and hope for tomorrow. So we can say, here I am, for now. And maybe that's the point. Because even if time is an illusion, it's our illusion. Even if light is a ripple through fields we barely understand, It's a ripple that warms our faces and lights our books. Even if C is just a number, it's the number that holds the stars apart just enough for life to breathe between them. So sleep now, knowing this: the universe did not choose to be fast, or infinite, or wild. It chose to be just fast enough, to make space for stories, and in the pause between one photon's birth and another's arrival, it made space for you, for something so vast, so mathematically exquisite. The speed of light doesn't exactly show up on your grocery list. You don't check it before you cross the street. You don't whisper it while brushing your teeth. It's not pinned to the fridge like a calendar or a child's drawing. And yet, it's everywhere. It hums in your pocket. It pulses beneath the touch of a screen. It keeps the beat behind every GPS pin, every video call, every flickering image bouncing between continents, while you barely notice. The speed of light, that immense cosmic constant, has quietly become the pulse of your everyday life. Let's start with something so common it's easy to forget: the internet. The moment you click a link or search for something or open this very video, tiny signals shoot off down fibre optic cables at nearly the speed of light. Under oceans, through mountains, between glass threads thinner than a hair, bursts of light race towards servers, translate your request and bring the answer back in milliseconds. You don't feel the distance, but it's there, measured in light moments, tiny delays too small for the mind to notice, but essential for everything to function. If the speed of light was slower, even by a little, everything would feel sluggish. Streaming, navigation, finance, communication. The invisible machinery of modern life depends not just on fast computers, but on fast light. And speaking of navigation, GPS wouldn't work at all without it. Satellites orbiting Earth send constant time signals, measured by atomic clocks that must account for both special relativity, because the satellites are moving fast, and general relativity, because they're farther from Earth's gravity. Those time differences are minuscule, just billionths of a second. But without correcting for them, your location could be off by kilometers. That's right. Your morning walk, your Uber ride, your stargazing app, all whispering thank yous to the speed of a light. But it goes deeper still. Think of how we speak about time, distance, and clarity. We say something happened in a flash. We talk about bright ideas. Someone who understands quickly is lightning fast. We fall in and out of the spotlight, and when we finally comprehend something, we say we see the light. These aren't just metaphors, they're reflections of something deeper. A cultural memory that equates light with truth, speed with intelligence, and illumination with understanding. It's no accident that across dozens of cultures, light is associated with insight, healing, and transformation. Religious ceremonies light candles not just for warmth or visibility, but as symbols, offerings, connections, prayers. Birthday cakes carry their tiny constellation of flames. Festivals string up whole galaxies of light to mark endings and beginnings. Children sleep better with a nightlight. Lovers fall into each other under the soft glow of street lamps. Light, in these moments, is comfort. Ritual, memory, but always, it moves. Not frozen, not waiting, just there, arriving. And in the background of it all is that speed, that invisible law that turns illumination into sequence, connection into timing. You may not measure it, but you feel it. You feel it when the lights flicker during a storm and the room changes texture. You feel it when the sun sets a little too early and the shadows grow unfamiliar. You feel it in that microsecond pause on a phone call when you realize the other person is thousands of miles away and their voice had to bounce off satellites just to meet yours. That delay, that whisper of distance, is the speed of light saying, "I'm working on it." And beyond the machines and metaphors, there's something even more personal. The speed of light shapes the way you remember. Look around your room. Everything you see, the lamp, the mug, the texture of the wall, is light that left those surfaces and entered your eyes, was bent by your cornea, and triggered chemical reactions in the back of your brain. All of it took time. Tiny slivers of time, yes, nanoseconds, if not less, but real. You never see anything as it is, only as it was a moment ago. You live ever so slightly behind reality's leading edge, and while your brain smooths over those delays, makes the world feel immediate and unified, physics insists that every second of your awareness is already in the past. You are a being made of echoes, which oddly enough might explain something about human emotion. Grief, for instance, is often described as a kind of delay, a part of us still catching up to what the world has already accepted. We struggle not with the fact that something changed, but that we didn't see it coming. We're always just a step behind. And enjoy, too, when something arrives suddenly, unexpectedly. There's a moment where we light up, like our minds and bodies are being caught in the act of reception. The arrival of a word, a gesture, a beam of sunlight through the window, it's all a gift of timing. Even love, perhaps, is about rhythm, about being present in the same light cone, sharing the same beat, too far apart in miles, in life, in readiness, and the signals won't reach, too close and the light might overwhelm. But when you're just close enough, moving at the right emotional velocity, something beautiful happens. You synchronize, and still, we chase more. We build faster machines. We want instantaneous everything. Delivery, response, download. We name our devices after light and speed and magic, and yet, some of our most meaningful experiences come not from fast things, but from waiting. Watching the first morning light spill across the horizon, catching the glint of gold on a tree at sunset, standing in silence as a lighthouse beam sweeps across the bay. Those moments move, but gently. They remind us that light's greatest gift isn't how fast it moves, but that it moves at all, that it has a rhythm, that we can notice. Even photography, the freezing of a moment, is a love letter to light speed. Every photograph is a timestamp of when the light arrived, not the object itself, not the person, but the light from them, stopped in flight. We hang these on our walls, not memories exactly, more like relics of reflection. And so, this number, this C, this 292,458 meters per second, becomes more than physics. It becomes a presence, a quiet, invisible artist drawing time's outline around everything we feel. It shapes the way we celebrate and communicate, the way we perceive beauty and distance and closeness. It determines how long it takes for a hug to be seen from space, how fast a goodbye fades, how soon a greeting reaches its reply. It even lingers in the way we speak of our futures. We look forward to the light at the end of the tunnel. We envision better days. We cast light on problems, brighten someone's mood, and shine in moments of joy. But we rarely ask, how fast does that light move? Because what we care about, deep down, is not the number, but the feeling, the arrival, the glow, the warmth. And that's the great irony. The most constant speed in the universe is something we feel as a moment, a flicker, an impression. Science tells us that the speed of light is a law, but we experience it more like a language, one that tells us, you are connected, one that whispers, here is what's real, just a breath after it happens, one that says, time is moving, and so are you. So the next time you walk through a beam of sunlight, or catch the blinking of a firefly, or squint up at the stars and wonder if they're still burning, know this. You are living in the gentle echo of light's journey. You are stitched into a rhythm that is shared by sun and screen, by galaxy and glance. And you are exactly where you need to be. One lightspeed moment behind now, and in that delay is everything. Let's play a game, not with dice or cards, but with reality. Let's imagine, just for a while, that the speed of light isn't a limit, that something, a ship, a thought, a whisper from the edge of time, could go faster. What would that mean? At first glance, it seems like a dream come true. A starship that could fold the galaxy in hours instead of lifetimes. A message sent to another world and returned before the sender even finished typing. But when you peer more deeply into the math, into the fabric of space-time, something strange and slightly unnerving begins to unfold. Because breaking light speed doesn't just make things faster, it breaks order. In Einstein's world, cause and effect are sacred. One thing follows another, neatly, even if clocks disagree on how long it took. There's a universal logic, enforced by the speed of light. But if we allowed something to go faster, truly faster than c, then one observer might say the message was sent before the sender decided to send it. The effect would precede the cause. A decision could ripple backward in time, and that opens the door to paradox. Imagine you send a message to your past self warning them not to make a certain mistake. They change course. But then, the mistake never happens. So the message was never sent. But if the message wasn't sent, then the mistake still occurs, and round we go. This is called the causal paradox, or the grandfather paradox when told with time travelers and family trees. It's the kind of loop that makes logic slip through your fingers. Our universe, as far as we can tell, hates that kind of thing. The laws of physics, elegant, stubborn, quiet, seem to arrange themselves in ways that protect causality. So perhaps that's why light speed is what it is, not just to limit how fast we can go, but to preserve the sanity of time itself. Still, science fiction dares to ask, what if? What if we could warp space instead of crossing it? Enter the warp drive, not the humming engine of a starship, but a theoretical idea grounded in general relativity. In 1994, physicist Miguel Alcubierre proposed a method of bending space, compressing it in front of a ship and expanding it behind, so the vessel itself doesn't move through space faster than light, but rides a wave of distortion, like surfing space-time. From the inside, the passengers wouldn't feel any acceleration. From the outside, they might seem to move faster than light. But technically, no laws are broken. It's clever, elegant, and wildly impractical, at least for now. The warp bubble would require negative energy, a kind of exotic matter with properties unlike anything we've observed. It might also collapse catastrophically if disturbed, or generate intense radiation. And even if we solve those problems, there's still this. It's possible that information couldn't escape the bubble once it began, that any message sent would be forever trapped, light unable to cross the edge, a one-way trip to somewhere, with no way to say hello once you arrive. Then there's the idea of wormholes, shortcuts through space-time, tunnels linking distant points with a curve rather than a line. Theoretically, they're allowed by general relativity. Solutions to the equations exist, but building one, keeping it open, that's a different matter. It might require the same kind of exotic matter, negative energy, quantum tricks. And even then, stability is uncertain. Some models suggest wormholes would collapse instantly. Others say they'd pinch closed the moment light tried to pass through. Still, the idea is tantalizing. Because wormholes don't just offer faster travel, they offer non-linear travel. You could emerge not just in a distant place, but a distant time. And then we're back in paradox. In theoretical physics, some models allow closed time-like curves, loops in space-time where a particle could, in theory, return to its own past. But again, something always seems to get in the way. Some say quantum decoherence would prevent it. Others propose chronology protection, a term Stephen Hawking coined to suggest the laws of physics conspire to prevent time travel. That, like bouncers at the door of causality, the laws of nature quietly step in and say, not here, not now. But what if they didn't? What if we could build a stable wormhole, a working warp drive, a tachyon communicator? What kind of reality would we live in? Here's one possibility. A universe not with one timeline, but many. Every change you make, Every paradox you create spins off a new branch, a new path, a new reality. This is the essence of the many worlds interpretation of quantum mechanics, that every quantum choice spawns a new universe, endlessly branching. In that case, a faster-than-light message to your past might not undo your present, but create a new one. No contradiction, just divergence, like parallel rivers flowing side by side, unaware of each other. This idea of multiple timelines, of branching histories, is a favourite of science fiction. And no wonder. It lets us imagine second chances, alternate selves, what-ifs and what-might-have-beens. It lets us believe that somewhere, somehow, there's a version of us that chose differently, that reached the stars, that sent the message, that heard it in time. And while that may never be proven, it's an idea that comforts. Because even if the speed of light locks us into one path, one present, one unfolding, our minds are not so limited. We can imagine faster. We can dream beyond. And perhaps that's the secret. The speed of light is a physical boundary, but dreaming has no speed limit, and yet, even science sometimes hints at the impossible. Take quantum entanglement. Two particles, once entangled, seem to affect each other instantly, no matter how far apart. Einstein hated it, called it spooky action at a distance. But experiments confirm it. The measurements are correlated. Change one, and the other responds. Faster than light could travel between them. Does that mean information travels instantly? No, because the outcome is random. You can't control what result you'll get, and therefore you can't send a message. But still, it's odd. It suggests that under the surface of space and time, there might be a deeper connection, a fabric not limited by distance, not bound by speed, a kind of timelessness that occasionally bleeds through, and that makes you wonder, what if consciousness works that way too? Not as a signal that moves, but as a presence that already is. What if awareness, the thing you're using right now to hear these words, isn't bound by time at all? It's a radical idea, not proven, but not ruled out either. And in the soft, speculative hours, the kind where thoughts stretch like shadows at dusk, it's an idea worth sitting with. That maybe light speed is the limit of matter, but not the limit of mind. And so, we come to the paradox at the heart of all science fiction. And all science. We want to move faster than light. We want to touch the stars, to time travel, to erase our mistakes, to send warnings, to hear echoes before the sound. But we live in a universe that says no, and yet, somehow, that no makes the yes more beautiful. Because in the space between what's possible and what's dreamed, we find something rich, yearning. And yearning, slow as it may be, is what gives meaning to time. So keep dreaming. Imagine starships that surf space-time. Imagine letters sent to the past. Imagine a version of yourself who made it in time. Just remember, even if we never outrun the speed of light, we can still outdream it. And maybe, just maybe, that's enough. Maybe the speed of light isn't just a number. Maybe it's a lullaby, a cosmic rhythm you've been humming your whole life without ever knowing the words. It's there when you open your eyes and see the morning light. Photons born 8 minutes ago in the sun's core now touching your skin. It's there when you glance at a distant star and realize the light you're seeing left long before you were born. It's there when you look in the mirror and for the briefest moment, see not exactly your present self, but yourself from a billionth of a second ago. Because even reflections take time, and that's what this has all been about, hasn't it? Time, and what we make of it. We began tonight by asking a question, gently, half whispered in the hush of evening. Why is the speed of light limited? Why should something so vital, so everywhere, move at such a precise, unwavering pace, never faster, never slower? And in chasing that question, We've wandered through strange and beautiful places. We've walked alongside Galileo on windy Tuscan hillsides, watched Römer track the flicker of moons, stood with Einstein as he imagined a boy riding a beam of light across the universe. We've peeked inside particle accelerators, stargazed through gravitational lenses, and pondered the very shape of reality itself. We've listened to photons whisper across space. We've watched as physics unfolded its quiet rules, that nothing with mass can ever reach the speed of light, that time and space stretch to keep the law intact, that light doesn't just move through the universe, it defines it. And we've seen how deeply it all ties into us. Because light is not just something we measure, it's something we live inside. Its speed is woven into the way your brain processes sight, into how fast you react, into how long it takes for you to feel anything. Every moment you experience is coloured, ever so slightly and by that speed. Not fast enough to be noticed, but fast enough to be real. And that matters, because if light were slower, the universe would feel sluggish, uncoordinated. Things wouldn't line up the way they do. Life might never have arisen. The very chemistry of cells, of energy, heat, electricity, all depend on how quickly information can pass from one place to another. And if light were faster, then reality might lose its grip. Events could become unmoored from order. Effects could arrive before their causes. Clocks could lose their meaning. The gentle flow of time, that dependable current, would become a storm. So maybe, just maybe, light's speed is a kind of balance, not arbitrary, not random, but tuned, delicately, invisibly, to allow something as fragile and strange as experience to emerge. We often speak of time as a river, flowing, endless, ungraspable, but maybe time is a mirror, and light is what moves between us and our reflection, between what was and what is seen, between what we are and what we understand. And mirrors, as you know, take time, just enough time to reveal us, not too fast, not too late, just enough. Think of how much we rely on that delay. Light leaves the sun, and 8 minutes later warms your skin. Light from the Big Bang, cooled, stretched, almost a sigh now, still hums as background radiation, telling us of the universe's first breath. You're surrounded by messengers, and all of them move at the same speed, because the universe has no hurry. Its stories are patient, its light travels on time. Even now, somewhere deep in the night, stars are exploding. New ones are forming, whole galaxies are spinning silently, throwing off photons that will not reach us for billions of years. And when they do, if someone is here to see them, it will be as if they're watching the past through a window that never needed hinges. The universe does not forget. It just takes time to arrive, and in this strange, looping way, the speed of light becomes a kind of memory, a soft delay that lets the cosmos remember what it has been. We think of memory as something stored inside our minds, and it is. But it's also out there, in the light still travelling from a kiss that happened beneath street lamps 10 years ago, in the glow of distant cities rising into the sky, in the slow, careful unfolding of flowers under spring sun that began its journey hours before. Light carries memory, and because it moves as it does, and not any faster, those memories stay with us. They don't blur into instantaneity. They don't vanish behind speed. They linger. Isn't that a kind of grace? That we're allowed to notice? That we can still see stars whose light left before the dinosaurs vanished? That we can build telescopes to catch light from galaxies whose shapes haven't existed in millions of years? That the universe lets us look backward without ever leaving the present? Maybe that's the most poetic thing of all, that we live not in a flash of now, but in a shimmer of then, always a little late, always just in time. So what have we learned? That the speed of light, that elegant sea, is not a limit to curse, but a rhythm to dance to, that it sets the beat for cause and effect, that it writes the rules of what can be known, that it shields us from paradox, from chaos, from the unraveling of story, but also that it makes room for mystery, for delay, for reflection, for the precious, quiet seconds between input and reaction. A message is sent, a breath is taken, a light arrives, and in that pause is where meaning lives. We are beings made of waiting, from neurons that fire just milliseconds apart, to lovers who wait for the reply, to scientists who measure stars that have long since gone dark. We are always receiving, translating, catching up, and maybe that's the gift, not to arrive instantly, but to have time to feel the journey. Light doesn't just illuminate things, it announces them. It says, this is here, this happened, this matters. And it never yells, it just moves, exactly as it must. So the next time you light a candle, or stare into the sky, or notice the way shadows soften in late afternoon, think of the photons making their way toward you. Think of the seconds they've travelled. Think of how long it takes for anything to reach you, and be glad for that delay. Because in that space between what is and what is seen is where you live, not behind, not ahead, but perfectly, beautifully, exactly where you are. So, where are you now? What time is it where you are? Has the sky shifted since we began? Have the shadows moved, even slightly? Maybe you're lying in bed, blankets tucked around your shoulders, or maybe you're just listening, eyes open, staring at a quiet ceiling. Whatever your moment looks like, thank you for sharing it, for pausing with me in the flow of light and time, for letting your thoughts drift gently without needing to hold on too tightly. It's a strange comfort, isn't it? Knowing that even now, while you breathe, while the world turns, while sleep gently approaches, somewhere out there, light is still travelling, still obeying the same rules, still making its way through galaxies and dust across unfathomable distances, all at the same unwavering speed. Nothing faster, nothing slower, just light, moving the only way it knows how. And here we are, tiny creatures on a tiny planet catching those beams, turning them into stories, meaning, music, memory. It's easy to feel small, but maybe it's also okay to feel small, because small things still matter. A single photon still makes a difference, and so do you. If this brought you peace tonight, even a little, I hope you'll consider liking the video, subscribing to the channel, or sharing it with someone else who needs a moment of stillness. But even if you don't, I'm grateful you are here. Truly. You didn't need to understand every concept, you didn't need to memorize the math. You just had to listen, to feel, to wonder quietly along with me. That's all science ever asks, really. Wonder, and the willingness to stay a little longer with the questions. So I'll leave you now, just as we began, gently, softly, with a quiet thank you whispered into the dark. Sleep well, fellow traveller, wherever and whenever you are.